lit. I'm sorry, the IT will come.
I think everyone is in the room now.
Yes,
so
everyone. Now?
No.
And now every button is lit. I'm sorry, the IT will come.
I think everyone is in the room now.
Yes,
so
everyone who wants to see it will be in the room. So I'm calling for the first presenter of this session, Raidan Bassa, who is applying ConvLSTM algorithm to forecast water levels in the Everglades. Please, the floor is yours.
Okay, thank you so much. My name is Raidan Bassa, and my thesis research is about applying convolutional LSTM algorithm to forecast water levels in the Everglades. So I'll start with a background and problem statement. What is convolutional LSTM? It's a deep learning model that is designed to deal with spatio-temporal data, tasks like video analysis and so on. It has two components, convolutional layer and LSTM. Convolutional layer, it's responsible for processing the spatial information, while LSTM is used to capture the temporal dependencies on the data. So in this research, this model is used to forecast the water level in the Everglades. The Everglades, it's a large wetland ecosystem located in South Florida in USA. It has an area of 20,000 square kilometers, and it's a home to a wide range of plants and animal species. As you can see in the map, the red line is the border of this ecosystem, while the blue line is the border of the case study area of this research. So this research is focused on a specific part of the Everglades. It's called EDN polygon. So the EDN polygon, it has an area of approximately 9,000 square kilometers. And EDN, it stands for Everglades Depth Estimation Network, which is a project that generates daily water level surfaces by using a network of gauge stations, as shown in the map, and also by using interpolation models to estimate the water levels among the gauge stations. So the research problem is forecasting the water level in the Everglades has very important role in managing this ecosystem, and also to help the water authorities to make informed decisions about restoration efforts, about water allocation and conservation strategies. However, there are two problems. The first one is the hydrological forecasting models face difficulties in simulating the complex hydrological system. On the other hand, we have machine learning models, which have high capability to capture such complex relationship. But there is still another problem, that most of the machine learning model used in the Everglades are ANN models, which are artificial neural networks that are point models that focus on specific gauge stations and did not cover a large area. So the objective of this research, the main objective is to evaluate and analyze the forecasting capability of convolutional LSTM by forecasting the water levels throughout the EDN polygon area, and also to assess the potential of using one convolutional LSTM model instead of using multiple ANN models for each gauge station. So to achieve the main objective, we have sub-objectives. The first one is to build one convolutional LSTM model. It's indicated as the global model. To build also two ANN models in two different gauge stations. They are indicated as local models. The purpose of building these local models is to compare the forecasting results of these local models with the global model. And the last one is to validate the global model with one of the existing forecasting tools that is in the Everglades. So the research questions, first is how does the convolutional LSTM model perform in forecasting water levels in the Everglades compared to the ANN models? The second question, is it possible to use only one convolutional LSTM model to forecast the water level in the whole area of the EDN polygon instead of using multiple ANN models? And finally, can the global model be validated by one of the existing forecasting tools? So here we have the methodology. So we start with data acquisition, and then we go to the data processing. Then we build the convolutional model, which is the global model. and then building the local AN models, and finally compare the forecasting result between them, and also to validate the global model. So we start with data acquisition. So as you see in the map, we have gauge stations that are in yellow colors. These gauge stations, they measure the water level and rainfall every day. And also we have stations that measure the outflow discharge from water control structures like spillways, pump station, culverts, and so on. So the data or the download data are the daily average readings of these stations. So we have three data type or data categories: water level measurement, rainfall readings, and outflow discharge data. These data are daily data that range between the 1st of January 2002 to the 31 May 2023. Now, the next step is data processing, so preparing the data for the global model, which is the ConvLSTM model. As I mentioned earlier, that ConvLSTM model, it deals with spatio-temporal data, like images, videos, and so on. For this reason, the data were prepared as raster maps. So in each day, we have 3 raster maps, one for water level, one for rainfall, and one for flow data. These raster maps have a resolution of 400 meters. So how I did that, for the water level, the download data are already in GeoTIFF format. For the rainfall, the download data, it was like time series data for each gauge stations, that it has daily average rainfall. So simply, for each day, we just did the interpolation method to convert the data to raster. So each day, I have one rainfall raster. For the flow data, it has the same idea as rainfall. We have time series gauge stations data. So first, we convert them to raster. But here we have extra step, which is clipping this raster with a mask layer of canals and streams. So the final format is only the pixels that intersect with canals and stream has flow data. Other pixels have zero flow. So now we have the 3 raster files are ready. Okay, in machine learning modeling, there is very important step which are data scaling and data split. So in this research, the data were scaled in the range of -1 and 1 using this formula, and also we calculated the minimum and the maximum for each data. For the data split, we split the data to 3 sets: validation set, test set, and training set. The validation set, it takes the first daily data of the 3 years. Test set, the second 3 years, and the remaining is for the training set. Here we talking about building the convolutional model or the global model. First, we talk about input variable selection. So the global model is built to take the data of today and yesterday in order to forecast the water level after 2 days. So for each day, we have 3 raster maps for rainfall, water level, and rainfall. So for today, 3 raster, for yesterday, 3 raster, so we have 6 raster maps as input. This model was trained and compiled using a Python library called TensorFlow, which is developed by Google to deal with machine learning models. So here we have the model construction. Here we have the input data, which are 6 raster maps. And then we go to the layers of the model. We have 1 convolutional LSTM model and 2 convolutional layer. And the output of the model is also a raster map that has a resolution of 400 meters that have the predicted water level after 2 days. These values of number of filters, kernel, and so on, it was, or they were chosen after doing an optimization algorithm using Python. Then we go to the local models. So 2 ANN models were built in 2 different gauge stations. One of these stations is affected by water control structure, which is S980, and the other one is not affected by any water control structure. So simply, we have the 3 input data, which is water level, rainfall, flow, for today and yesterday, and the predicted, or the output is the predicted water level after 2 days. Okay, now about the results and conclusion. I'll start with the global metrics information. So 2 metrics we have: mean absolute error and the coefficient of determination, which is R squared. So we calculated these two metrics by using the test dataset, which range between the 1st of January 2005 to the 31 December 2007. By using this formula and by using also the raster calculator, we got these two raster maps. This raster is for the mean absolute error, and this is for the R squared. So as you can see here, the mean absolute error is range between 6 millimeter to 11 centimeter, and most of the location have an error less than 2 centimeter. While for the R squared, most of the location have more than 0.9 R squared. Now we compare the global model to the local model, starting with the station BCE4. So as you can see here, we have the forecasting results of the global and local model compared to the measured. We also have the matrix information for the global and the local model. And also we have the main absolute error for both models, local and global models. It can be noted that both models perform approximately the same, but the local models here show better results. But there is a reason behind that. The local model was trained to forecast the water level in the gauge station itself directly, while the global model was trained to forecast the water level on the raster pixel, which is above this gauge station. So of course, these two values are not 100% the same because of the interpolation process. The measured data here that is used here in this comparison is the gauge station readings, which the local model trained to forecast. For this reason, the local model here show better results. The same idea with the second station that is affected by water control structure. As we can see, the local model show good metrics information than the global model. But now if we compare the forecasting result of the global model to the measured data of the pixel values, and we compare the local model to the gauge station readings, what we will get? We will get these values. So now every model is compared to their training targets. We get this information. As you can see here, we have the mean absolute error for both model in station BCE4 and here for station S980. As you can see in the matrix information, they are approximately the same. So we can conclude that the global model and the local model, they have approximately the forecasting accuracy. Here we compare the global model to one of the existing forecasting tool in the Everglades. It's called EverForecast. The EverForecast is a statistical and a hydrological model that simulates the water levels in the Everglades for the coming 6 months. Here, the comparison between the global model and EverForecast for 2-day lead time. The forecasting lead time is 2 days. As you can see that the global model show better results than the EverForecast. And also here we have the matrix information. So finally we go to the conclusion. So the ConvLSTM model in this research show a good performance, a better performance than the EverForecast tool that is in the Everglades for short-term lead time, which is 2 days. The second conclusion is the ConvLSTM model and the AN model have the same forecasting accuracy when they compare to their training targets. Here we have also the ConvLSTM model show high capability to be used as one forecasting model instead of using multiple ANN models. My recommendation first is to extend the forecasting lead time beyond the 2 days by incorporating predicted rainfall from the European Center for Medium Range Weather. Also to evaluate the forecasting capability of ConvLSTM model by comparing it to other machine learning models like time-delayed neural network or to LSTM to have more analysis of the ConvLSTM capability. And to also to conduct an uncertainty analysis on the ConvLSTM model output to improve its informativeness and utility. I think I still have some time, so I want to thank my supervisor, Professor Bishwa, and my mentor, Dr. Jirab, and also thank for everyone who attended my presentation, whether in this class or online. Thank you so much.
Thank you, well ahead of time, but we will only use the 10 minutes in view of being fair with everyone. So we will start with our external examiner, please.
Yes, thank you for your presentation. Well, it's amazing to see such a good performance from your spatial convolutional LSTM.
Thank you so much.
Yeah, so well, I'm just curious. Why do you use LSTM in your thesis? I mean, there are also convolutional neural network, for example, could probably also do the same as a special sort of recognize the spatial pattern, you know. And so I'm missing a bit from the presentation. Why LSTM in particular was chosen in,
Yes,
compared to other?
we want also to use the time sequence data, which is because we will use the data of today and yesterday. So we have time sequence data. That's why we need LSTM. And convolution is for the spatial analysis, and so that's why we use the LSTM to take the data of previous days.
Okay, and you showed your training, testing, and validation data split. That was 2 year, 2 year, and
3 years,
yeah.
and the remaining is for the training.
Could you explain a little bit more why do you choose that splitting strategy?
Yes,
why
because
the first 2 years, etc.?
Okay, so because I want to preserve the timeline, because I use LSTM, I use the previous days data, so I cannot split them in like randomly way.
No.
Or statistical way.
Yeah.
So I need to split them in the timeline way, in intervals.
Mm-hmm.
So the first 3 years is for validation, the second 3 years for test, and the remaining is for the training. As you can see, the percentage is 14, 14, and 72. So it's only to preserve the timeline. That's why I split them in.
Is there any special consideration in view of, let's say, extreme events occurred in those 2 years, whether there are more extreme events in certain split? There are less in another data sets, because I can imagine that will affect the training quality and also the validation, right?
Yeah, actually the extreme events is happening in the 3 sets, but like not the same, approximately not the same. But I cannot like do the statistical analysis because I need to put them in that way. So if I did the statistical way, then I will lose my timeline.
Mm-hmm.
So I cannot do this statistical approach.
Okay.
Yeah, to preserve the timeline.
All right. Thank you.
Thank you.
Thank you very much. No, it's okay.
Me? Okay, thank you.
Yes.
Can you maybe go back to your map whole area, and where are the points that you are forecasting, water level?
You mean the first one?
Yeah, maybe. Yeah, for example.
This one?
Yeah, so this is, you said, the wetlands, right?
Okay, let me go to. Yes, it's
So-
wetland.
So in your global model, where are you forecasting water level? Everywhere?
Everywhere, yeah.
And
Because,
so that means you assume there are always water?
Yes, because it's a wetland ecosystem. So yes, I assume there's like water level everywhere. Because between the gauge stations, the data that I downloaded already have water level values between the gauge stations.
And your the station measurement points are in the inflows points or the canals in between these passing through the wetlands, or how are they? So these are the 2 stations you are saying?
Yes, I chose these 2 stations like randomly in order to compare it with the global model to see if the global model perform well or not. But the global model it forecasts everywhere.
And measurements, where you have measurements? You have also many places within
Yes, everywhere, like even
measurements. Measurement stations also you have many places, or
I'm sorry, I didn't get you.
measurement,
Okay.
observation, water levels,
Uh-huh.
where are available?
Yes,
within
This is the gauge
Or
station.
these all blue are?
Yeah, are the gauge
okay,
stations
okay,
that
yeah,
measure
okay.
the water levels.
So your comparison then is
Yeah.
the global model comparison is against all of these points.
Exactly, exactly.
Okay, okay, then I get it. Okay. Yeah. So then that's I think very interesting use you found with that global model forecast, which must be very efficient in that case. Only thing I was now a bit concerned, or not concerned, but I don't know if you had a chance to look at. You want to you forecast basically only water level, but your inputs you took 3, and the water level and discharge.
Right.
So I wonder how much you gain adding taking discharge and water level both just to forecast water level, because they must be very much correlated, and I wouldn't be surprised if you get similar result if you use only water level, not add discharge, if you are forecasting only water level.
Yeah,
Have you
because
looked at in that level?
yeah, if you can see here, for the outflow discharge, it's only for the places that has like rivers and streams. So of course, because of the outflow, these places like canals and streams will be affected by the water control structure, by the flow of water control structure. Other places like
No, I understood you forecast only water level, right?
Yeah,
Your
exactly.
targeted forecasting water
Yeah,
level,
yeah.
not discharge.
yeah, but the discharge is one of the input.
Yeah,
Because-
that's my question.
Yeah.
So I would, have you tested how much you gain adding discharge together with water level
Mhm.
to forecast water level? That's my question. Would you probably get similar or not if you only had water level instead
Because
of
the
adding
procedure
discharge?
of building the global model takes very long time, like more than 3 days. So to try with like using only water level, I don't think I could do that. But like I use the water control structure because it's logically affected the canals and the streams.
Okay.
First, a very small, quick question. The order of magnitude of the error. So you talked about 2 centimeters. What is the total range you see in the data set, more or less, on different water levels? Because I have no idea if it's a lot or a little.
Yes, even as a reference. Actually, the purpose of this research is to compare the forecasting of ConvLSTM to ANN models.
Yeah,
So-
that I understand.
Yes, so there's no clear reference to the main absolute error, is it good or bad, but because the purpose is to compare with the ANN model.
Yeah,
Is they are performed the same or not?
That I understand,
Yeah.
but in the end you have a raster image you produce, so there's a range in, for instance, the minimum and the maximum water level in that raster image, right? So could you give me, is that a lot, is that a little, is it meters, 10 meters of difference between north and south, for instance? I have no idea. Or you don't?
Yes, I mean, if you can, I think like less than 2 centimeter is good result, because
Yeah, that's the error.
yeah, because the average differences for each.
But you produce a raster image with water levels, right?
Yes.
Yeah. So what's the range in those observed water levels that the raster outputs, more or less? Do you have an idea? Did you check that quickly?
You mean the water levels values?
Yeah?
Yeah, it's like between 250 to 1300 centimeters.
250 and
2 meters.
300 centimeters, the water levels.
1 meter kind of difference.
No,
Or
no.
no? What is the
No,
difference?
I mean the range of the water
Yeah.
levels.
Yeah, yeah. So,
So-
what is that?
200 centimeters to, what did you say?
So the values of the water level,
Yeah?
like in one day, in
Yeah.
specific day. For example, it has here like 250, 260, and some places that they have 200, 300.
Okay.
But centimeter.
Mm-hmm. Yeah. Okay. And, well, this took quite long, so.
Okay, no. Well, you were mentioning that you want to extend forecasting lead time, yeah, based on your results. And do you expect that they will perform as good as here, what you have done, or do you expect that you will have some different type of results?
I think it depends on the predicted rainfall that they will use, because they need to use predicted rainfall to use the same idea. So if the predicted rainfall is like good data, maybe but of course they're not going to get the same accuracy. But if the predicted rainfall data is good, they will get good results.
And another question that maybe they are not using a global model now, they are using local models. You in 3 months succeeded to do such a good global model that predicts everywhere, starting from all the data that they have. Maybe you don't know the answer. How come that they did not go for such, because they are using all kind of methods, all kind of models, they are so advanced. How come that they are not yet using, or did you have some previous references or studies that you looked at that use this and you just started from there? So can you?
Yes, they have like such global models, but in like hydrological models that simulate the hydrological system of the Everglades. But as a machine learning model, or especially ConvLSTM model, they, as in my research, I didn't find anything like that.
But do you have a, maybe it's too much to ask, do you have a reason why they would not use?
I will ask them.
You ask them.
Basically, she asked a Louis van Gaal question. Are they so stupid or are you so smart?
Well, not really, but okay. Well, we can take a question from the audience, if there is any question in the audience. You have a follow-up question, please go ahead with a follow-up
So
question.
well, that relates maybe a little bit to what Joanna just said, and it brings you maybe a bit outside of your comfort zone, and that is about the usability. Now you created a big machine learning model for the area, which works very well. Let's say the hydrological model doesn't perform so well. Would that have implications for the policies and the responses they might have? Because so in other words, what are the bad sides of a big machine learning model that works very well in terms of responses, etc.?
You mean the drawbacks? Or?
Yeah.
Maybe because between the gauge stations, the forecasted or the water level will not be as accurate as like in the gauge stations. This is one of the drawbacks. And also, as you can see in the map, like some location, the global model face some difficulties on forecasting the water level. For example, here you see the error is high. Also there, the R square is really low. So there are some places the global model cannot forecast the water level in high accuracy. So this is like some of the drawbacks.
But they only had the local neural network models, or they also had a global model that was...
As a hydrological model, yes.
Yeah, exactly. But that's of course a very explicit model. There is the physical system is in there, and this is a black box.
Yeah.
Right? So it's more difficult to, in the end, create the responses maybe, because you don't know which factors in the end contribute to the problems in the forecast. Okay, thanks.
You also have a
Yeah,
follow-up,
perhaps a
please.
question related to that comment. But you show that they do have a hydrological model, but I think you explained very quickly. It's a statistical-based hydrological model. But my question is, to model such a wetland, shallow water system, you probably want a hydrological in combination with, inundation model or the 2D shallow water type of solver to simulate the water level at every single pixels. So my question is, I don't know if that model exists, but I would be very curious to see the performance between your AISTM and with that physically based shallow water model.
I think ever forecast that compared with the global model of research is one of these like hydrological. It's hydrological and statistical model that simulate water levels throughout the Everglades. So I compared this model with my global model, with the global model.
Yeah, I know it's a hydrological model, but I'm not sure how physical.